All right. So, as our final foray here into the kinematics of the particles, purely describing motion, let's see, what have we talked about, right? We've introduced the idea of position, velocity, acceleration. We talked about how those relate in straight line movement along a one-dimensional path that can only go forward and backward. How that, in that scenario, scalar quantities are sufficient, but as soon as we go into curving paths, we need to go to vector quantities for position, velocity, and acceleration. Describing those vector quantities can be done in a Cartesian coordinate system, a natural coordinate system where we're in normal and tangential components, and then the polar coordinate system. The last little bit we need to add on here is this idea of relative motion, and we'll use this little diagram I have set up here of an Earth coordinate system that we have fixed, Earth fixed coordinate system. Let's say I just add Earth fixed coordinate system, and then a plane flying overhead. And what we'll do here is, in this section here, talk about the relative motion between 2 points in a reference frame. But just know one of the key ideas here is we can actually extend the ideas here to talk about how to convert description between reference frames going forward. Okay, so we have this scenario. Maybe it's like the classic example with, the plane flying, and so there's definitely motion of this, what we could choose as a different coordinate system, right? So we want to just look at the kinematics, describe the motion within the plane. We don't care that there's a fixed Earth out here. Let's fix our coordinate system to something inside there. So in fact, let's do something. So we have like the pilot, which is always fixed because they're responsible for flying the plane. So let's say up here is a person B. Let me just draw their head, I guess, is all I can fit. Oh, who cares that they... Right. Okay, so there's the person B there, and the person A is going to be the one in the back. And let's say they're like walking to the rear of the plane. Okay, so well, let's just have this out. Consider passenger A walks to rear of plane while the pilot B moves with the plane. I mean, they both do. They're both on the plane, right? But pilot B is fixed, right? Moves with the plane. I'm just say fixed to represent pure motion of the plane reference frame relative to the Earth reference frame. Right? So the pilot represents the motion of the plane reference frame compared to the Earth, relative to the Earth. Okay, so the question we might want to ask here, or the goal we're trying to get to, is how to relate something like the velocity of A relative to the plane, that's B, and the velocity of A relative to Earth, which is O. Okay, so we have these two things, velocity of A with respect to B, and velocity of A with respect to the Earth, which is O. So two different coordinate systems in that case, right? Okay, so let's see here. So the position vectors to these two important points for the Earth reference frame, right, is going to look something like that, and like that. So this is RA, down here is RB. These are in the fixed Earth coordinate system, right? And well, okay, let's write those out. Okay, RA and RB, these are positions of A and B as seen from, so relative, as seen from the origin. So what we say is with respect, well, let's say relative or in terms of, relative to Earth coordinate system. And it gets extra complicated in thinking that the Earth actually rotates, but we'll ignore that for a second, right? Or ignore that and talk about that in due time. Okay, we then go back to the diagram here and say, well, who cares about the Earth and those position vectors? I mean, we care, right? That's the part of the question here. But if we ignore that, we just want to know how is A moving with respect to B. Well, that looks like this, right? So how does B see A's movement? Right? And that's that thing there, which I don't want to crowd this too much, which I have a tendency to do here. This we're going to call is the position of A with respect to B, not in terms of the fixed coordinate system or the primary coordinate system, which is the Earth, but just from the plane's or the pilot's perspective, which is the plane reference frame origin. Okay, so this RA, and this is a new notation, and we're going to see this a lot. So this is our time to just talk about it and think about it. This is the position of A as seen from B. Okay, now note here, these are just, 2 points in this other coordinate system. All we'd have to do to talk about what's the position of B as seen from A, or with respect to A, well, that's just flip the vector around. Right, so that's something we can always do. Okay. So with this, let's talk about basically answering this question here. This is just one of the questions, which is about velocity. Let's start with doing this with position. How do the position vectors, because there we have them down there, right? We have the position vectors all on the diagram. We can start there, and then taking a derivative will give us the velocity, which actually answers that question, and then we'll even extend it to acceleration because we can and we will need to. So this is the to get position, all we have to do is notice that we're doing vector addition here. Okay, so you see here, right, how do we get to A? Well, we can go RA, getting to A from the origin, or we can travel along RB and then go backward to RA. Well, it's not really, it's be adding it on. It's just backward in our picture, right? So through vector addition, RA is the same as go to RB, and then from that fixed point, or from that point in that other reference frame, add on the relative motion. So this is our relative motion, right? And so that's it, right? And the other things fall out pretty naturally. Velocity. How do we get to velocity with this relative motion? Well, the velocity of A is just going to be its derivative of its position vector. So this is the velocity of A with respect to the Earth coordinate system, kind of the primary coordinate system. Well, that means we took a derivative of this left-hand side, so then we take a derivative of the right-hand side. All we do is add dots to the top, right? Or, better said, if we want to know the velocity of A, we just take the velocity of B vector and add on the relative velocity. So this is the velocity of A as seen from B, which might be different, right? Here, right, the velocity of A with respect to B is straight backward, right? But the velocity of A with respect to the Earth, with the Earth organ, so like this would be in the exact. Okay, so these this would be the velocity of. This is the velocity of A, which is straight back, but the actual velocity seen here at O is going to be not the backward motion, but we take the backward motion of him walking to the back of the plane, plus the very fast speed of the plane going forward, right? Well, that's the velocity of B. So what we're doing is taking the velocity of the plane and adding on the relative motion to go backward, right? Yeah, let's actually put that down here. So for our example, the velocity of the passenger, so passenger A, as seen from Earth is going to equal the velocity of the plane itself, which is probably much bigger than this second term here, plus the velocity of that small velocity of the passenger walking to the back, as seen from the plane fixed coordinate system. Right? So in our example, what this says is that the actual velocity we would see of person A is not as fast as the velocity of the plane because they're walking to the back. Now, once they're done going to the bathroom or whatever they're doing at the back of the plane and they walk again forward, it looks like they're actually walking faster or moving faster than the actual plane itself, right? So we're just adding on these components. Okay, the last thing, do this one more step, pretty trivial. Acceleration vector from for A. This is the pure acceleration from the primary coordinate system, so from the Earth. This would be, in our example, is going to be the acceleration of the reference frame itself plus the relative motion inside that moving coordinate system, or that moving reference frame. Okay, so let's do some examples how we can use this. I mean, the actual ending relationships aren't that complicated. What's tricky is knowing, what are the two different coordinate systems? What are the two different motions in a reference frame that we need to consider? So I think going to an example is going to be key here. Okay. Okay, so in the first example, we have an airplane that's pointing due north. I need to be careful with this word pointing. So the airplane is flying due north. Okay, but then there's a wind coming, and the wind is so it's kind of moving. The airplane is moving fast at 560 miles per hour. We'll draw pictures for these, but I'm just starting here. And then the wind is coming at 30 degrees north of east. So like that, right? And the absolute motion of the plane is then going to be something that's like that, right? Okay, as it gets blown by the wind. So let's break this down in order to use our relative motion analysis here. And we'll draw like a little kinematic diagram for the plane first. Okay, so the plane itself just has this motion. So this is the velocity of the plane, but the plane with respect to the wind, right? To the air, right? It's moving straight as if it was in stagnant air, would be just flying straight there. But it's not just stagnant air. The actual system around it, the air it's flying through is actually moving. And how is it moving? Put our X, Y, or maybe this is east and north, right? Is moving off in this direction. So this is the velocity of the wind. So this is the velocity in which the plane is moving. So the actual system in which the plane is moving, I think the reference frame in which the plane is moving is heading off on that direction, okay? And then let's add in the actual speeds. The velocity of the plane with respect to the wind, not the vector, we're just talking about the speed, is 560 miles per hour. And then the velocity of the wind itself is 60 miles per hour. Okay, so our relative motion. Oh, and what do we want to determine the ground speed? So there's some little vocab here. What we're saying here is if you're an Earth observer, what does it look like the airplane is moving to you? And in which direction is it heading? It's trying to point north, but again, it's not going to be exactly. It is pointing north and flying north in the moving air. Because the air is moving itself, it kind of trends in a easterly direction, right? Okay, so our relative motion says that the velocity of the plane from an observer on Earth, right? So that's going to tell us the ground speed and the course, right? Think right already, right? The magnitude of this is the ground speed. The direction of this is the course. And that's it. All we need to do is determine the two components here, and we can determine its magnitude and direction. Well, this is going to be the velocity of the wind, the motion of the air mass that the plane is flying in, so the motion of the reference frame for the plane, and then this relative motion of the plane within the wind. Okay, let's see if we can get a good diagram of what, combine these two diagrams basically into one. Okay. Okay, so again, this would be x and y, or east and north. Okay, let's write it like this. North of east. Yeah, that's right. Oh yeah, okay. Okay, course. Yeah, actually, I need to be more careful with what the course is. Okay, we'll come back to that. So here's the wind. It's actually quite small in magnitude, so I'm even exaggerating this. So this is going to be 60 length. All right, so the magnitude of this vector is like 60, and then we have to add to it purely in the y direction the plane at 560, so it should almost be 10 times bigger. That's why this isn't to scale. All right, this should be longer. So this one is purple. This one here is the wind. Okay, and so if we add those two together through vector addition, and that's why I put the tip to tail here at the back, this here is that vector, the actual velocity of the plane as seen from an observer on Earth. And the course, what we're actually looking for, is actually this angle. All right, so the course of the plane is how much is it deviating from its intended, well, from its pointed direction, right? Which is pure north. So its course is how much it's deviating from that. Okay, so that's course, theta, and then the magnitude. Okay, so I'm going to simplify our notation here and just go to simple subscripts. So the velocity of the plane with respect to the wind is actually 560 j hat. Our velocity of just the wind is 60, right? But actually add to our diagram here. All right, you got a little triangle there where the hypotenuse is magnitude 60. So the I hat component is cosine of 30 degrees I hat, and then sine of 30 degrees gives us the j hat. And then cosine of 30 degrees, show you like my little trick here. I know that this is going to be either root 3 over 2 or a half from my knowledge of the unit circle. I always draw it out, and I know 30 degrees is there-ish. The x component and the y component, one of those should be a half, right? So sine is the y component, that's a half. I see I don't have these things memorized, I just remember this. I do this every single time. And this one is root 3 over 2, because that's not the half, that's more than a half, right? Remember, on a unit circle, the coordinates here are cosine theta, sine theta, so your x component is cosine of whatever angle. Well, that's bigger than a half, right? Because I went to 30 degrees. All right. Okay, so the velocity of the plane is then going to be velocity of the wind, which is 60 root 3 over 2 I hat plus a half j hat plus 560 j hat. That's your velocity. That's the relative motion of the plane in the wind. So therefore, our velocity of the plane is 51.96 I hat plus 590 j hat. So definitely mostly, oh, went off the screen there. Definitely mostly in the direction, you know, of the where it's pointing, right? It's much more j hat than I hat, but we do have some tending into the I hat direction. So if anything, it would look like this, right? Very slowly trending away, right? Getting off track. Although they, you know, maybe off track, they're probably the pilots know this, right? And they would account for it by pointing the plane, right? So this is, maybe they're exactly on track. Maybe they anticipated a stronger wind, and so they actually course wasn't exactly aligned, and so they need to even turn even further this way, right? All right, getting too real here. All right, so take the magnitude of that, right? That's 51.96 squared plus 590 squared, square root the whole thing. I'm not going to write out the magnitude. We did it in our earlier videos. Okay, but the thing we actually haven't done, I don't think, is talking about this course. So let's kind of go back to this diagram and maybe zoom in on it a bit. So And our course is going to be, now the two components matter here, because what we have is, okay, exaggerating the angle. It's actually going to be much smaller than this. Here's our course angle. We know that this is 590, which tells us the length there. Maybe I should draw it over here. This is 590, and this is 51.96. Okay, so the course is going to be given, so the tangent of theta is 51.96 over 590, and so taking the inverse tangent of that other side, we get 5.033 degrees. So 5 degrees, right? So instead of, I think a lot of this talk has been like, well, we're going off track here because of the wind. No, the pilots now, they're doing this calculation. They're saying, it's like, how far do we have to, we want to go in at 5 degree angle. Is it okay to fly directly north, right? Or, some sort of calculation like that would go into the calculation. Okay, that's it for this one. All right, so in this second example of looking at relative motion, we don't have an airplane like we've had, I think, in everything so far. We have two cars traveling at a constant speed around circular tracks, so they each have their own constant speed, and they all and along two different tracks, so two different radiuses. Let's see, car A is sitting out here on the outer track, has that radius and that instantaneous velocity, or instantaneous speed, I should say, and constant, right? And then B car is right there, having a little bit closer in and a faster speed. And then at this time instant, the angle from B to A is 25 degrees. So, theta is right there on the x-axis. Okay, what we want to do is find the magnitude of the velocity and acceleration vectors of the B's motion relative to A. So from A's perspective, how is B moving? The way we'll do this is, and it's going to be convenient because of the circular motion, to do this in polar coordinates. Which, by the way, I don't think I said this in the previous lectures. Like, in circular motion, polar coordinates are the natural coordinates, right? We have E hat r and E hat theta in purely circular motion are the natural and tangential coordinates. Okay, and then now this down here for B is going to be its version as well. Okay, that's going to become important because these are not the same, yeah? So I don't want to, this is its own version of that. Let's just keep that in mind, yeah? Okay. So let's get our relative motion relations down here and we'll talk about it. If we want to know B's motion relative to A, we'll write it like that. And that goes for acceleration as well. Okay, so rearrange both these. We just need to find the absolute motion of B and subtract off A in terms of the fixed coordinate system, which I guess, right, has this central origin O there. Alright, so we can describe the motion of A and B independently. We just subtract them and we got their relative motions. Okay, this is where it gets where we have to be really careful. Right? So if we choose polar coordinates to do this, okay, then we would need to make sure that they are the same coordinates. Right? Basically, if we're going to subtract two vectors, they have to have the same vector nature. They have to have the same base vectors that we're using to describe, to represent those vectors. So in order to subtract the vectors like we need to do here, the base unit vectors have to be the same. Okay. So what we're going to do here, the approach is going to be to write them out because it's so easy in uniform circular motion to use polar coordinates. It's going to be so trivial to write out what VA and VB and AA and AB are, right? We can subtract them, but in order to subtract them, we need to convert them in their individual ER, E theta coordinates, convert them to Cartesian, which is a fixed thing, right? So, and in fact, you can see that's going to be really easy for B, right? For B's position, the polar coordinate is the Cartesian coordinate here. So later on, right, we need to basically write them both in terms of their Cartesian coordinates. Okay, so let's do this for A, and we'll see that B is pretty trivial. So we're going to start in polar, which is also the natural coordinates here. And isn't it great, actually, when we get to B, all three coordinate systems are the exact same. Cartesian, polar, and natural are all the same. A is not the case, but polar and natural are the same here, right? Okay, so the velocity vector is the speed only in the theta direction, and the acceleration of A is, oops, sorry, RA times its angular acceleration in the angular direction minus VA squared over RA E hat R. So that's our expression for the acceleration in polar coordinates here. Now we have constant speed, so that's 0. Omega A is constant because we have constant speed. Okay, so our acceleration in polar coordinates for A is minus VA squared over RA E R. So let's see. This is a good version of this. And what I mean by good is we know these quantities, right? Those were given. These are known quantities now. VA, RA, VA there. All right. The thing that's kind of not really known, although we have enough information for it, obviously, we're going to solve it, is these two guys, right? Now, if we were adding this and subtracting it to a vector that was right in line, and we knew that they had the same unit vectors, they were pointing in the same direction. We know it's not true because they're not, right, in our diagram. But if they were, we wouldn't need to do any more work with this. We would then move on. Okay. So B, similarly, VB equals the speed of B in the theta direction, and acceleration of B is minus VB squared over RB ER. Basically, you'd run through the same exact thing. Write down that the acceleration, the angular acceleration is 0, cancel that one out. Okay, so we have what we need. Why are my B's looking so disjointed there? Okay. Looks like a 13, doesn't it? Alright, so we've got our four relationships, and we should be able to plug those in. It looks like that would be the mistake, right? Because this is not equal to that. This is not pointing in the same direction as that. So if we were truly the most, this is A's version, this is A's version, this is B's version, this is B's version. Okay, but they're getting a lot of subscripts there. So this is where we have to be really careful. These base unit vectors are not identical between A and B. So what are we going to do about it? Okay, we convert them to Cartesian. Okay, so first for A, the theta is going to be, this is the normal one, right? Normal to the motion. E hat theta is going to be minus sine theta I plus cosine theta aj. So we've talked in the past, we've worked through this these conversion to Cartesian in the past. Minus sine 25 degrees I hat plus cosine 25 degrees j hat, and the radial unit vector, the expression is cosine I hat plus sine j hat, which cosine 25 degrees I hat plus sine 25 degrees j hat. Okay, so our vector, right? Our vectors are vectors in space, and it's just our choice in how to represent them in terms of the base unit vectors. This is going to be, so we're given that VA is 36. We actually want to start plugging in numbers now. Times, now instead of E hat theta, right, this is E hat, and we're going to write it in terms of its IJ components. Minus sine 25 degrees I hat plus cosine 25 degrees j hat, and we get minus 15.2143 I hat plus 32.6271 j hat. Right, so you can check that calculation if you wish. And then our acceleration vector, v squared over r. So for a, that's 36 squared over 1250 feet. And here we're going to plug in now, instead of E hat r, it's converted to Cartesian. Cosine 25 degrees I hat plus sine 25 degrees j hat, and we get minus 0.9397 I hat minus 0.4382 j hat. Okay, gotta go to a new page. I'll keep the end results there, still on the screen. Okay, now we move into B, right? We gotta also convert B's unit vectors over, and we're gonna be rigorous, right? At this point, I hope you can look at this and know that E hat r should just be the I direction. Go back to the diagram, right? The radial coordinate should just be along x, so therefore our unit vector along the radial direction is just in the I hat direction, and then normal to it, E hat theta, is going to be purely in the j direction. But we can make sure, right, convince ourselves that this is true by running through the same procedure as we did here. E hat theta equals minus sine theta b I hat plus cosine theta b j hat. But theta b here is 0 degrees, so sine of 0 degrees is 0, cosine of 0 degrees is 1. J hat. Good, right? Check our work. E hat r, cosine theta b I hat plus sine theta b j hat. Here, sine of 0 degrees is 0. Cosine of 0 degrees is 1. So this is just I hat, as we are just confirming, right? Okay, great. So VB is then just 45 j hat, because the speed is given as 45, and our acceleration is going to be minus 45 squared over 1200, just plugging in the given quantities here, all in the I hat direction, which is minus 1.6875 I hat. Okay, we've got it now, right? So let's see. Now we're going to be plugging things into here. This is we quickly got to these vectors. That wasn't hard. Polar coordinates allows us to get to these really fast. What we spent most of our time is converting these to the same base unit vector so we could add them together, or I guess subtract them, right? What are those things we're going to plug in? Well, it's right here. Where is it? Right here. Right here. Right here. And right there. And we've got it. Yeah? Okay. Plug into original relations. It's that box, that square box, those that I just highlighted. VBA is then 45j hat minus negative 15.2143 I hat plus 32.6271 j hat, which is, this is B relative to A's motion, 15.2143 I hat plus 12.3729 j hat. Feet per second are our units. And well, we need the magnitude, right? So that's going to be components squared. So this squared plus that squared, square root the whole thing. We get 19.61 feet per second. And then do the exact same thing for acceleration. I'll just do this quickly. Okay, I added them together, or I guess subtracted off A's acceleration from B's acceleration here. And we get this as our components for the vector. Now to take its magnitude, right, components squared, square root the sum of the two squared components. And we get 0.8667 feet per second squared. And that's it. Now, before we close this off, which we are done answering the question, let's just look, right? What this right here says, you know, this is a little bit tricky. We could talk about that, but I want to focus on this. This says that from A's perspective, B is moving in the I hat direction and the j hat direction. Okay, oh, that's negative. I was going to say that actually doesn't make any sense. Negative, and this one makes sense to be positive. Okay, so from A's perspective, right? From A's perspective, as B starts moving at this point, right? It's going to start moving that way. Well, at this instant, though, it's moving straight up and down, right? So it doesn't matter that it's going to be trending along a path. That has to do with its acceleration at this point. Its instantaneous velocity is in the j hat direction, absolute, right? From the absolute O's reference frame, right? But from A's perspective, since A is moving that way, right? A is moving to the left. It looks like B. Oh, that is plus. Okay, I have to go back. This is a plus. I forgot that negative sign there, right? I made the mistake. Whatever happens when you try to go explain, get some intuition at the end here. I really love doing this here, right? And then this is 45 minus 32. Okay, great. Okay, let's take a step back, right? This is plus. I made that mistake. We now are back on track. As A is moving this way, right, it looks like B is, even though it's not moving any further in the I hat direction, relative to A it is, because A is moving kind of towards the x equals 0 point, right? So as A has a component that's kind of backwards to the left, even though B isn't moving at anything left or right, it looks like to A that B is moving to the right. It's because A's absolute motion is to the left, right? Okay, and now, you know, this motion here, 12 being up, well, that comes from 45. That's pure B's motion, and then there is the upward motion of A. B is moving up faster than A is moving up, right? So it looks like A, from A's perspective, it looks like B is kind of approaching it in the vertical direction. Yeah? So right there. These are our two components. Because A is moving to the left and upward, B is only moving upward, but faster upward than A is moving. From A's perspective, it looks like B is moving to the right and moving upward, right? Okay, those are kind of the nice analysis you can do at the end of a problem like this. Now, this wraps up our study of pure kinematics here. We're ready to move into talking about the forces that cause these motions. But we spent a long time relative to the course here. This course devotes a lot of time to kinematics alone, and doing it in a very complicated, rigorous way. And so this is a big tool set that doesn't go away. We're going to use this as just a part of the full dynamics analysis to come.